All right, friends, welcome back. In this video, I'd like to go ahead and start Chapter 3, and you can see here that Chapter 3 is going to talk all about polynomial functions. So as we make our way through the chapter, we're going to discuss everything from quadratic functions to other types of polynomials, trying to find zeros of polynomials, and also how to use polynomials to model mathematical situations here. So I'd like to go ahead and start that by taking a video lesson here over 3.1, which is going to discuss quadratic functions. And then, yeah, we'll just kind of take a look here. So quadratic functions, they all can be written in this same general form. This is called the general form of a quadratic. And the most important part of a quadratic is that x squared term, which is why down below here you see that we've included this extra note that a is not allowed to be the number 0. Okay? If it was the number 0, then this whole entire x squared term would fall away, and we would just be left with bx plus c, which is a linear function instead of a quadratic. So that x squared term is the most important term of this entire function formula. Some things you may remember about quadratics is that number a is actually pretty important for being able to talk about what the shape of the graph actually looks like. You may remember that any quadratic function has the shape of what we call the parabola, and we'll talk a little bit later about why the parabola has its shape, but for now, if playing the role of a is something that is a positive number, the thing that you need to remember is that the parabola is going to open upward, and if your a is a negative number, then of course we have a parabola that opens downward. Okay, and then let's actually talk about why the parabola has its shape, right? Well, it all has to deal with the parent function for quadratics, which is sitting right there in the top left-hand corner. That's y is equal to x squared, okay? And so the idea there is any amount that we move horizontally, x, we are going to move the square of that vertically, which is y, okay? And so you can see that I've drawn a little bit of a diagram here to demonstrate that, right? So if I sprout out from the vertex down below there a matter of 1 unit to the left and to the right, we would go up from there a matter of the square of 1 unit, which of course is 1. If I sprout out 2 arrows from the vertex, then I'm going to go up the square of 2, which is 4. And if I sprout out 3 arrows, I go up the square of that, which is 9. So what I'm going to do here is try to, hopefully OneNote will be nice to me and let me go ahead and select this so I can copy it. And what I want to do is go ahead and take this shape and actually transform it. So it looks like I copied everything there. That's pretty good. Just going to go ahead and select copy here. And then paste with any luck. We'll actually get another copy of this. So let me go ahead and do that. Possible. Oh, there it goes. Perfect. Okay. So we have a picture of this guy that we can go and move around freely here. So in that first example, what it's going to say is, if I scroll up to it here really quick, it's going to say that we want to take our parent function f of x and then subtract a 4. So f of x is equal to x squared minus 4 here. So we'll go ahead and do that in blue because I have that done in blue there. That's going to be following my colors here. That's pretty good. And then, of course, this is where your original function formula would land, is at a vertex of 0, 0. But, of course, we want to go ahead and shift that down 4 units. So that means that every point here is going to be shifted down 4. And so if I shift down 1, 2, 3, 4, I, of course, would land right here. And, you know, actually, I'm just realizing now that that skeleton is not drawn very nicely onto my grid. So we'll go ahead and get rid of that and just go ahead and draw it. Tried to be fancy here in the video, and it's not working out for me. But the idea is going to be maintained, right? We're going to shift the vertex down 4 units and land right there. Sprout 1 to the left and right and go up 1. Sprout 2 to the left and right and go up 4. Sprout 3 to the left and to the right and go up 9, etc., etc. Okay? And that's why the parabola does indeed get that shape there. So we can just go ahead and approximate the rest with a nice smooth curve. Drawing both sides. It's a very symmetric shape. Symmetric with respect to the y-axis here. We could fold half of it onto itself over the y-axis and it would overlap perfectly. Same thing in all these other ones here. We would just go ahead and simply want to do the same for all these others. So in the case where we have g of x, which is x squared plus 5, I would just go ahead and shift everything up 5 units. Okay, so the vertex was at 0, 0. I'd go ahead and shift that up 5, so I'd be about right there. And then I'd follow the same general skeleton pattern for my parabola. So sprout 1 to the left and to the right, go up 1. Sprout 2 to the left and to the right, and go up 4. Gives me a nice and easy general shape just like that, and go ahead and approximate the rest with a nice smooth curve. In the case of that next one, we have h of x is equal to the quantity x minus 3 all squared. Okay, so remember that we are taking 3 away from the input, and so that is going to shift us horizontally. And so the vertex, we're going to go ahead and shift that to the right 3, and then follow that same general pattern. Sprout 1 to the left and to the right, go up 1. Sprout 2 to the left and to the right, and go up 4. I don't believe we have quite enough room, or maybe we do. Let's see. Sprout 3 to the right and go up 9. Oh, yes, we do. Very good. And then we can go ahead and do the exact same thing to sprouting to the left and then going up that many units. Okay? So again, approximating the rest of this with a nice smooth curve. Trying to fit all these graphs in the same picture is going to be a big pain, but at least the colors hopefully will help us there. And then, of course, doing the last one there in green, we've got the quantity x plus 2 all squared, okay? So that's going to shift us to the right 2 units. And so my vertex would actually land right there. Sprout 1 to the left and to the right, I'd be at these locations. Sprout 2 to the left and to the right and go up 4, I'd be at these locations here. And then, of course, sprout 3 to the left and to the right, I would be at these 2 locations here, okay? So pretty easy to create the entire picture of the parabola if you know how the pattern of the shape works. That's going to be pretty good, okay? So, again, having all of those functions graphed in the same window is a little bit cumbersome to look at one individually, but the idea is that we have that idea going for each of those examples here where we're shifting, right? Switching gears from shifting, we might go ahead and now talk about how we scale vertically, because remember that whenever we change that number in front, that is going to either perform a vertical compression where our parabola is getting wider, or perform a vertical stretch where our parabola is getting narrower, okay? And so in order to graph these, what we would simply want to go ahead and do is the same thing. We don't have any sort of vertical shifts or anything like that, so we're just going to go ahead and go back down here to my example. We would just go ahead and start at the vertex, which is at 0, 0 for my parent function. And now what we would want to do is this. In this f of x, we have a 1/3 as our a. What's going to happen here is what we're used to doing is sprouting 1 to the left and 1 to the right and going up the square of that distance, right? Well, what we're going to do is we're going to go 1 to the left and 1 to the right. Instead of going up the square of that distance, we're going to go up 1/3 of the square of that distance. So if I sprout 1 to the left and to the right, I would be going up a full 1, but now I'm going up 1/3 of that, which would be 1/3 of 1, which is, of course, 1/3. So I'd be approximately right there. In the case of sprouting out 2 to the left and to the right, originally I would be going up 4, but since I have that 1/3 out front, I would be going up 1/3 of 4. So 4 over 3, that turns out to be 1.3333 repeating, and so that is basically just going to be 1 1/3, and so I would just basically be at these locations here. And you could start to see how the skeleton is going to work out because, again, if we go ahead and do the 3, that would be going up 9, but I'm going to go up 1/3 of 9, which is going to be going to actually 3 and there right there as well. So you could start to see how this is going to be different from your parent function. We'll go ahead and plot the parent function here just so we can compare. It's going to be a vertical compression here. Okay, so our vertex is there at 0, 0. Our parent function would go up to 1, 1, 2, 4, and then 3, 9. Okay, so you could start to see here why. Let's see, I would have that one there as well. Okay, so you can start to see there how we get this this vertical compression here. Okay, everything is going to be compressing vertically, and we are going to end up having this general shape right here where we are getting wider, of course. So let me try that again, trying to draw the rest of that parabola. And it's not the most beautiful looking parabola in the world, but the idea is that we just get the point, right? So parent function is there in gray, and then the vertical compression there is in pink. Okay, in purple, let's go ahead and do that vertical stretch. So again, the idea here is that now we have 3 times x squared. So if I were to start at the vertex here, now what I would be doing is sprouting 1 to the left and to the right, going up 1, but now because of that 3 in front, I would be going up 3 times 1, which of course is at 3. So if I sprout 1 to the left and to the right, I would be going up to 3 instead of just 1. If I sprout to the 2 to the left and to the right, I would be going up 4, but then that would be sprouting up all the way to 3 times 4, which is 12, which would be completely off my grid. And so you can kind of see here that the larger the number that you have out in front, the longer that vertical distance is going to be whenever you try to plot this thing, and that is why we get a vertical stretch. And of course here I am needing to make sure that I switch pens here, if that is a possibility. OneNote, maybe. we get a very much narrow parabola in that case, okay? So just being able to remember these cases where you have this number playing the role of A, that's going to correspond to a vertical compression versus a vertical stretch, okay? Another classic form that quadratic functions are going to be written in is what you call your standard form. A lot of other textbooks call this the vertex form, and the basic idea here is the reason why is simply because we would have a, let's see, is OneNote going to allow me to write here? Come on, man. Okay, let me try restarting my my OneNote here. But hey, you roll with the punches, right? So let me try to see if I can restart OneNote. Here it goes. Sorry for the delay. Okay, hopefully now I can write with my pen with any luck. There we go. Perfect. Okay, so as I was saying, the vertex form, or the standard form, is going to give you everything that you need to know about what the parabola is going to look like once you transform it, because it's going to tell you where the vertex is going to be. All you have to do there is take a look at what's playing the roles of h and k. That is going to tell you the coordinates of your vertex. And then playing the role of a here is the exact same a that was in our general form, where it's going to tell you about vertical stretching versus vertical compression, and also tell you about reflections here as well. Okay, so just don't forget, again, because a is being played by the same number there, that anytime your a is positive, that means you're going to be opening up in your parabola. Anytime that your a is negative, you're going to be opening down. So we would have these respective pictures, roughly speaking, there. And if you have your vertex form, again, it's super easy to figure out what your vertex is because you just figure out what's playing the roles of h and k. But if your quadratic is given to you in your general form, you're going to need to remember a little bit of a formula for you to be able to figure out what the vertex is going to be. So the x-coordinate of the vertex is going to be this little formula here. That's the opposite sign of b, all divided by whatever 2 times a is. And what you're seeing here is f of that as well. So that's just going to be the input and output, and then plotting that as an ordered pair. Okay, and of course, since your parabola is either going to be opening up or down, the lowest point you can be on the vertex, if you're opening up, we call that a minimum. And then the highest point you could be when your parabola opens down, that is going to be called your maximum. So later on, when we dip this into the context of an actual real-world example, we might be very interested in the highest value of x, or sorry, the highest output value that we can get out of our parabola, or the lowest output value we would get out, okay? So example 3 here, it says, write the quadratic function f of x is equal to x squared minus 4x plus 7 in standard form, and then find the vertex and y-intercept and sketch the graph, okay? So if we start off with that general form function, f of x, again, is equal to x squared minus 4x plus 7, the way that we would want to go ahead and write this in your standard or your vertex form is we would want to go ahead and follow that process of completing the square that we discussed in a couple of videos ago, okay? Although in this context it's going to look a little bit different because we don't have an equation to complete the square with, we have a function to complete the square with, okay? So what I'm going to go ahead and do is rewrite this function, leaving a little bit of space. And what we need to remember is that strategy that we had for being able to complete the square. And so you remember when we talked about it initially, we talked about how you need to take that b term and cut it in half and square the result. So our b term here, of course, is going to be negative 4. And so if I take that negative 4 and I cut it in half and square the result, then what would I get? Negative 4 divided by 2, cutting in half, that's going to be negative 2. And if we square the result, that's going to give you a positive 4. So for that reason, on both sides of this plus 7, what I might do here is go ahead and say plus 4. But I can't just introduce that without just changing the overall function. If I just left it at that, then this would be x squared minus 4x plus 11, because that's what 4 plus 7 is. So what I need to do is I need to introduce this plus 4, but also introduce something else to where I'm not going to be changing the original function. So if I just introduce a plus 4, then on the very end of this, I'll introduce a minus 4 to just kind of keep things maintained and not changing what I was originally given. Because what this is going to allow me to do is it's going to allow me to take this trinomial right here and rewrite it in that form of the binomial squared. We're going to go ahead and rewrite that as the perfect square, x minus 2 squared. And now the second part here, this is going to be something that we can actually go ahead and evaluate. So 7 minus 4 is simply going to give us plus 3. And now this is in your vertex form. So f of x is equal to x minus 2 quantity squared plus 3, this is the standard or the vertex form of that parabola. And we could look at the function written in this way and immediately pick out what the vertex is going to be. The vertex is going to be the point with coordinates 2, 3, because that's what's playing the roles of h and k. And then, of course, playing the role of a is just going to be that number positive 1, which is no different from the parent function, which means that we don't expect any sort of reflections or vertical scale changes here. So in order to plot this, what I'm going to go ahead and do is first figure out what my y-intercept is going to be. They actually asked for that in the problem here as well. And don't forget that the y-intercept is the point with coordinates 0 as its x-coordinate, and then the output of an input of 0 as its y-coordinate here. So if we figure that out real quick, might be something that you could do mentally, because oftentimes plugging in 0 is something that's pretty straightforward. Up here, if I plug in 0, then you can see here that the first terms are just going to go ahead and turn into 0, just leaving me with a positive 7 here. So the point with coordinates 0, 7 is going to be the y-intercept here on my graph. So if I come over here, that'll be one of the first points that I plot. I'm just going to go up here to 7 and plot that point. Let's go ahead and plot your vertex here as well. So that was the point with coordinates 2, 3, and then what we should find is that that y-intercept is actually going to be a point that sprouts out from the skeleton for a parabola that we discussed earlier. So sprout 1 to the left and to the right, go up 1, sprout 2 to the left and to the right, and go up 4. You can see that that kind of is where my my y-intercept would land, and then we don't have enough grid squares to go ahead and complete the rest of that skeleton that we said, so we're just going to go ahead and approximate the rest with a nice smooth curve in that way. Okay, so anytime that you want to rewrite a general form quadratic into the standard form, you're going to have to do that process of completing the square. So let's go ahead and demonstrate that here one more time. So in this case, I have f of x is equal to negative x squared minus 2. I'm going to leave a little bit of space and say plus 4. Now, before you complete the square, one of the things that you need to make sure that you have is a leading coefficient that is positive. So because playing the role of a is a negative number here, what I might do to start this off is I might just go ahead and factor out a negative 1 from everything. So what I might do there is just simply say x squared minus 2x, leave a little bit of space. Or actually, that'll be a plus 2x since I factored out a negative 1, right? And then later on, instead of saying plus 4 after leaving a space, I'll say minus 4, of course, and then leave a little bit of space in my parentheses there, because it's at this point that I want to go ahead and think about how I might complete the square. Remember, that's taking your b number and dividing it by 2 and squaring it the result. That'll give you plus 1. But again, I can't just introduce that without changing the original function. So if I introduce a plus 1, then later on in my function formula, I'm going to have to introduce a minus 1 to keep things balanced. Okay? And so, again, this same reasoning is going to apply to this trinomial here. We're just going to go ahead and rewrite that as the binomial squared. So the binomial x plus 1 squared. And then we also have what the constants end up being out here. So that's going to be negative 4 minus 1, and that is, of course, going to give us minus 5. But don't forget that this was all contained inside of a group that we factored out a negative 1 from. So if I were to distribute that negative back in, then I would have here negative quantity, x plus 1, all squared, and then plus 5, and that would be the standard or vertex form of this quadratic. Okay? And so, analyzing this a little bit, if we take a look and see what's playing the role of h and k here respectively, I believe that's going to be the point with coordinates negative 1, 5. And then playing the role of a is actually going to be a negative 1. And so don't forget that that corresponds to a reflection over the x-axis. Okay, so whenever we go ahead and figure out what this parabola is going to look like on the graph, we're going to need to account for the fact that this is going to be opening down instead of opening up. Okay, calculating the y-intercept here really quickly, we just need to remember that be the point with coordinates 0 as its x-coordinate, and then f of 0 as its y-coordinate. And maybe even a little bit of an easier way to figure out what f of 0 is to actually plug it into your standard or your vertex form up here, okay? Because that would only require that we'd have to plug in 0 in one place as opposed to many here. So if we go ahead and do that, using a little bit of mental math, we might go ahead and figure out here that 0 plus 1 is just simply going to be 1. Square that, you're going to get 1. So this is going to be negative 1 plus 5. And that is going to give us actually 4 here. So the vertex is going to be a point with coordinates 0, 4. And that'll be one of the points that we plot in addition to our vertex here. So let's actually go ahead and do that. So over here, we'll plot that point with coordinates 0, 4 as our y-intercept. And then we'll plot the point with coordinates negative 1, 5. Okay, and so if that's our vertex, then remember that this is going to be a parabola that opens down. So when we follow the skeleton pattern for our parabola, instead of shifting up, we're going to be shifting down here. So if I sprout 1 to the left and to the right, I would go down 1. If I sprout 2 to the left and to the right from the vertex, I would go down 4. Okay, sprouting 3 to the left and to the right from the vertex, I would go down 9. So count down, let's see, 1, 2, that'd be about right there. And then that means I'd be about right here too. And then we can even probably fit the one for 4 in here, right? So if I sprout 4 to the left and to the right from my vertex, I would be going down a matter of 16 here. So let's go ahead and go over 4 and then go down 1, 2, I'm just counting by 4s. It looks like it's just going to be just off the grid, so probably approximately be about right there and about right here. And that will, of course, just give us a little bit of a better idea of where this is going to end up off the grid. And we can go ahead and approximate the rest of the parabola in this way. So there we go. Not too bad. All right. So again, whenever you want to rewrite a general form into a standard form, you're going to have to complete the square. Example 5. So here we're given the graph, and now we need to come up with the actual function formula. And so because the vertex form is that form that kind of helps us translate from the function to the graph, let's go ahead and start with that form here. All right. And so again, all we're going to have to do is figure out what's playing the role of h and k. That, of course, is the vertex, and that's given to you right here. So h and k are going to actually be the numbers 1 and 2, respectively. And so I can go ahead and immediately, straight away, plug those in. So 1 and 2. So f of x, or a matter of fact, I'm going to go ahead and actually trade that out for a y for a reason that'll become clearer here in just a moment. I end up this far, okay? Now, the way that you want to continue here is you're not done until you've actually figured out what is playing the role of a in this problem. And in order to figure that out, it looks like the only unknowns in the equation besides a are x and y, and luckily for us, over here in the problem, they gave us a couple of coordinate points that our parabola passes through. And just remember that these are going to be a relationship between an x-coordinate and a y-coordinate. So those actually give us numbers to plug in for x and y, and the reason that I might pick that 0, 0 point is because, again, whenever you choose to plug in 0, things get nice and easy to simplify, okay? So 0 minus 1 is negative 1. Square that, you get positive 1. So this is going to be positive 1 times a, or just a, plus 2 is equal to 0. And then if you were to subtract 2 from both sides, you would get that you have an a value here of negative 2. And it makes sense that our a value turns out to be negative because, of course, we're opening down here in our parabola. And also, if you look closely here, because that a is 2, if I were to go ahead and sprout 1 in both directions for my vertex, instead of going down 1 originally, like we were used to, since that a is 2, I'd be going down 2 and plotting those points. And then I'd end up here at my x-intercepts. So that does make sense that a should be negative 2. And so now that we know all of our unknowns, we can go ahead and write our complete function formula here. F of x is equal to negative 2 times the quantity x minus 1 squared plus 2. And a way that you could check that is you could plug in the x-coordinates of your points and see that you get the corresponding y-coordinates as your outputs of this function. Okay. Number 6 is identical to the problem that we just did, but instead of actually giving you a graph, I'm just handing you the information here. I'm going to go ahead and just do this really quickly just because sake of time, right? So h and k are the vertex, and of course we give you a point, which is x and y. So if I start off with y is equal to a times the quantity x minus h squared plus k, then I'm just going to plug in my information and solve here. So 4 is equal to a times 0 minus 2 squared plus 3, and then I'm just going to go ahead and solve this for a. So 0 minus 2 is negative 2. If you square that, you get positive 4, so I could change this to positive 4a plus 3 is equal to 4. If I subtract 3 from both sides, then that's going to give me 1 on the left-hand side is equal to 4a on the right-hand side, and then divide both sides by 4, and I get that a actually turns out to be a fraction, 1/4. Okay? And so now that I have all my unknowns, I can go ahead and write out the complete function formula here, complete with the a value and my h and k. I'm going to go ahead and write that out as 1/4 times the quantity x minus 2 squared plus 3, and that will complete the problem. There is your function formula that has that information. Okay? As a little bit of an ACT prep question, it's really interesting here that we need to take a look at the parabolas that are graphed and kind of take a look at the information that's provided here. Now, one of the things about the ACT is that what they will do is, in words, they will explain everything to you that is information that you could just go ahead and find in the graph later on. But it is useful to go ahead and actually read the question here. So which of the following would be the general equation that defines this family of parabolas for all of the n's that are greater than or equal to 1? So, in other words, what is actually going on here? Well, you can see here that as n gets bigger, what is happening to my parabola? It looks like it is becoming more and more vertically stretched, or in other words, it's becoming more and more narrow, okay? So we just have to take a look and see what we've got going on here. One of the things that you'll notice about each one of these function formulas is that they all have this +1 at the end, with the exception of part C, and that +1 accounts for the fact that we have shifted our parabolas up 1 unit. And so what that's going to mean is that we can immediately eliminate the choice C from our choices. The other thing that you might notice is that on parts D and E, you have some A values that are, of course, negative. And remember what we talked about before about how if that A value is negative, then that means we'd have a bunch of parabolas that open down, but you can see here in the picture that they all open up. And so we can eliminate the choice D and E there pretty much immediately, which leaves us with A and B, which the only difference is, playing the role of A, right? The number in front of x squared. Is it going to be n or is it going to be 1 over n? Well, we said corresponding to a vertical stretch or a narrowing would be a number playing the role of A that is going to be greater than 1 if you were to take the absolute value of it. And of course, that is not going to correspond to choice B. That would be a vertical compression in choice B. So we would go ahead and have choice A there. So if you know your characteristics about parabolas, that's a problem that you can do in a matter of seconds if you're in an ACT scenario. And then the last example that I want to go ahead and take care of here in this video is an actual word problem here. So it says the profit P in hundreds of dollars that a company makes depends on the amount X in hundreds of dollars that the company spends on advertising according to the model P is equal to 230 plus 20X minus 0.5x squared. It says what expenditure for advertising will yield a maximum profit, okay? So I always recommend that whenever you have a word problem, you read the question first, and because the question here has a lot of economics jargon, we might just go ahead and look back into the problem and realize that what we have here is a model that relates P, the profit, with X, the expenditure, okay? So it's asking what expenditure, so basically what is X when we have a profit, which of course is capital P, and then they use this word, right? So they use this word maximum, okay? Well, let's make some sense out of this. So the model that we were given is not written in the standard general form here. So we might just go ahead and rewrite that as a little bit more of a standard form. So negative 0.5x squared plus 20x plus 230. Whereas if we write it that way, you might be able to recognize this is your general form of a quadratic, and playing the role of A is some sort of negative number, which means, of course, that if we were to graph it, it would be a parabola that, of course, opens down. Now, remember from before that the vertex of this parabola, since that is the highest point the parabola reaches, we would call that a maximum. Okay, and because they're asking us for a maximum profit and the output would be profit, then all we need to go ahead and do is find the vertex, and then we're going to be right as rain here. So let's actually go ahead and find the vertex of this. We can do that in a couple of different ways here. We can go ahead and convert this to your vertex form and pick out those coordinates of h and k if we wanted to. But an easier way to do this would be to remember that the formula for the vertex whenever your quadratic is given to you in general form is the following, right? So maybe say v for vertex. That would be an x coordinate that has a formula, the opposite sign of b over 2a as its x coordinate, and then just simply f of that as its y coordinate, so opposite sign of b over 2a. So what is b and what is a? Well, playing the role of b is going to be 20, so if I do the opposite sign of that, it's going to be negative 20. And then if I do 2 times the number playing the role of a, that's going to be 2 times negative 0.5, and so that is going to be negative 20 divided by negative 1 effectively, and that's going to be a negative divided by a negative, which makes it positive, and we'd end up with positive 20 there, okay? If we were to actually go ahead and plug that into your function formula, then we would get the maximum output, which is the maximum profit, but remember that the question didn't ask for the maximum profit, it asked you for the maximum expenditure, okay? Or sorry, the expenditure that yields the maximum profit, which we know that now. That is going to be a matter of 20, okay? So interpreting that in the context of the problem, because X was given to you in hundreds of dollars, we just need to go ahead and multiply that times 100 to actually get the actual answer in terms of the context of the problem, which would be 20 times 100, or in other words, that would be $2,000 that you would spend on advertising. So very important to be able to read the question and make sure that you're not doing more work than you need to do to answer the question there. So that's all I have for this video. Sorry it was a little bit of a long one, but again, just doing a nice overview of all the different things that you know from previous algebra classes about quadratics. So I hope this video has been of some help to you. Please, as always, let me know if you guys have any questions whatsoever. But that's all I have for this one. Thank you very much for your attention, and I will speak to you guys in the next one.